Okay, welcome to we're getting close to the end, week 9 webinar. And so what the plan is today, as always take questions if you have any questions as they go on. And that could be about the project, or it could be about what we're talking about today, or anything else, I guess. And then after that, we're going to get into, as you might notice from the list of items, they all say the first two words, chi-squared. So what we've pretty much focused on for the entire quarter so far, just about, is when you have a quantitative survey question. So that's when the answer is like a number, or when you have a yes/no survey question. Is that it? Are there any other kind of survey questions besides yes, no, and quantitative? Any thoughts? Let me ask you, what's your favorite color? Okay, yeah, you didn't say 17. You didn't say no, right?
Yeah.
Give me a word. Do you see? So that's going to be the main focus on chapter 11. And those kind of survey questions do happen a lot, and not just what's your favorite color, but that one's an easy one, unless you're like me and you're like a really nerdy physicist, and I think of colors as numbers, but most people don't. Yeah, I won't get into the physics, but there's some, for physics, color is numbers. So just trust me, or look it up somehow, and do some hard physics. But other things that you might ask besides what's your favorite color might be, what state were you born in, or what country were you born in if you weren't born in the United States. It could be, what is your ethnicity? That would be, again, it wouldn't be a yes, no, it wouldn't be a number answer. What's your major? That would be one, again, not a number, not a yes, no. There are lots and lots and lots of survey questions that are qualitative, not yes, no survey questions. And we need to be able to deal with those because we want to be able to analyze them and understand the statistics from them. So we're going to I'll start off just quickly talking about the chi-squared distribution. We've had a lot of different distributions in this class. We've had, if you remember, we had the binomial distribution, the uniform distribution, and then we had the biggie. What's the most important of all distributions? It's the biggie. Let's see, I'm jumping in. The normal distribution. Hopefully, that's the most important of all of them. And that's because of the central limit theorem, which says anytime you do a survey with quantitative data, the sampling distribution is always normal, okay, if you have a large enough sample size and it's unbiased. So there's a normal distribution. Then we had the t distribution, students' t distribution, and that was when you didn't know because you don't usually know the population standard deviation, and you still want to find a confidence interval, do a hypothesis test, and the way to handle that is the students' t distribution. And today, we're going to be using a new distribution called the chi-square distribution. Okay, and I usually see it as chi-square instead of chi-squared. I wouldn't take off points if you wrote chi-squared, but for some reason, I have no idea why they don't put a D at the end. So we'll talk about the chi-square distribution, and then we'll use it. And we're going to use it with 3 different tests. The first is going to be a chi-squared goodness of fit test. None of this stuff is going to mean anything to you right now. It's just words, right? But it's really important if you want to say, does the distribution fit something known? Then you use a chi-squared goodness of fit test. Then we'll look at the chi-squared test for independence. And the chi-squared test for independence is when you have 2 qualitative survey questions and you want to find out, well, if you know something about, you know the answer to the first one, does that give you information about the second one? So that would be like, let's say the question is, what is your ethnicity? And the second question is, what state do you live in? Let's say we're asking people in America. Well, if you know their ethnicity, does that help you understand a little more what state they might live in? And the answer is yes, actually, it turns out, because there are certain states that have a higher percent of certain ethnicities. And if you don't know that, trust me on that, but you probably know that. Okay, and so again, depending on what the ethnicity is. So there's a test for independence to find out are they independent or are they dependent. And then finally, we're going to be doing a chi-square test for homogeneity. And that's a lot like the goodness of fit test, except with the goodness of fit test, you're looking to see if this population that has the same distribution as something you know. Whereas the homogeneity is we have two distributions. We want to find out if they have the same distribution as each other when you don't know either of them. Okay, so a lot like chapter 9 versus chapter 10. Chapter 9 is when we had, say, we want to find out the proportions greater than 50%. Well, 50%, we know that number is 50%. But we don't know, something else that we want to find out, compare with 50%. Versus we have two different groups and want to say, does one group have a different proportion than the other group of what we're interested in? And that would be comparing two unknowns. So that's what goodness fit versus homogeneity is. It turns out mathematically, which you don't have to know, turns out independence and homogeneity have exactly the same mathematics. Mathematically, 4 and 5 are the same, real similar. But in terms of ideas, 3 and 5 are real similar. So that can get confusing, I guess. But you're going to be, as you're used to by now, I'm sure, you're not going to do the deep mathematics. Instead, what do you think you're going to use?
The calculator.
Yeah, you're going to use the calculator, okay? You're going to use the calculator. And by the way, before there were good calculators for this, okay, or even before there were calculators, people don't even do this. It was just too hard. Yeah, like no one would do these things, or not normal people at least. So calculators really brought up statistics and made statistics a main subject to learn to be able to understand stuff. Before calculators, it was really too hard to do. So statistics was hardly ever even taught because it was too brutal. But with calculators now, it's not that bad. I know it might be a hard class, but the mathematics is not that bad, right? You just pop in the calculator, but you have to understand what it tells you, but the mathematics isn't too bad. And then just a note, I put this here. So chi is a Greek letter. And it may look like an X. It kind of looks like an X, doesn't it? It may look like an X. Technically, it's not. It's a chi. Okay, and again, don't get mad at me. I'm not the one that names or decides these things. I'm just tell you how the statisticians do things. And the squared, as I mentioned, there's a lot of deep math in it. So the only thing that you should know about the square, can you square a regular number and get a negative number? No. If you take a regular old number like 73 or negative 40 or whatever, and you square it, you will always get a positive number. And what that means, as opposed to say the normal distribution, is that when you have the chi-squared distribution, you're only going to have a right tail. It'll always be skewed right because it stops at 0. There's nothing to the left of 0. So you don't even deal with a hypothesis test that has a less than or a greater than. You only talk, you just don't go there. You don't have to worry about the type, whether it's less than or greater than or not equal to. None of that even happens in this chapter. So just let you know, and in fact, this chapter, your hypotheses are going to be sentences and not symbols. Because symbols, one, they don't tell the story as well, and the other is, in the old days, we used to use symbols, and then students could never get it. It's no good if everyone fails. So we went to words. So for this chapter, it's going to be H0 and H1 are going to be in words. Okay, just a note. Okay, any questions about anything? Okay, any questions? I do want to mention something that I know that there's some people looking for project partners. So if you only have 2 people in your group, then, and you see in the project discussion board, somebody saying, I need a partner, please, strongly consider letting that person in, because it's a good thing, and make that person do work, by the way, and then you have less work to do. So just note, because I saw on the project discussion board that there's a few people looking for partners, and that happens. Okay, so take a look at that. Any questions? Any questions? Okay, figure maybe I'll take a look at this. Let me do this, I think is easiest. There we go. So I created a little visualize the chi-squared distribution calculator, not calculator. So it turns out there's something called degrees of freedom, and that has to do with pretty much how big your sample size is, or size is. The bigger the sample size, the more degrees of freedom. And with different degrees of freedom, you get a different picture. Okay, so you'll notice that here is the graph, and you'll see it starts at 2, 4, 6, 8, 10, etc. And there's no negative number shown. And hopefully you understand why, because chi-squared can't be negative. So there's no reason to even have that shown. If we have fewer degrees of freedom, then it's very skewed. Do you see? Okay, and if you have 1 degree of freedom, it's as skewed as get. If you have like 15 degrees of freedom, what's it starting to look kind of like?
A bell.
Yeah, bell. Slightly skewed to the right, more than the bell, right?
Yeah.
But that's because my degrees of freedom have gone way up. Okay, and it's not really the sample size quite as much. It's not really the sample size. It's more of the how many different options there are for answers. So if someone asked you, if the question was, what state were you born in? Then the degrees of freedom, how many states are there in the United States? See if you know.
50.
Yeah, so it turns out degrees of freedom is 1 less than that would be 49. So it'd be really high. Do you see that? On the other hand, if someone asked you, what season were you born in, winter, summer, spring, or fall? Then degrees of freedom would be 3, 4 minus 1. So that makes a big difference in what the chi-squared looks like, because that would be 3 degrees of freedom. Whereas 50 looks almost normal, right? 15, somewhat normal. 50, you can't even tell the difference. Okay, but I figure I'd show you because that's what we're doing. We're doing the chi-square distribution. Any questions on that? The mathematics is even, I believe, too hard for Braulio. I don't know, Braulio, you ever seen the math of the chi-square distribution? Yeah, it's really, really tough. It's
never have.
Yeah, you gotta have like a master's in math at least to truly understand it. It's tough. Normal distribution's a little bit hard, but not like the chi-squared. So I'm not going there. But if you want to become, if you want to get a master's or PhD in math, then you could learn about it. So right now, just trust me that there's the picture. Okay, and it has something to do with the normal distribution in a weird limit way of thinking. I'm not even going there. Sound good? And there's a square that happens, as you might guess, since it's called chi-squared. Okay, so again, I just wanted to show you what it looks like because I think it's good to see. So these are really best done by example. So let me give you an example, and we're going to do a kind of example of each type. A couple of goodness of fit, it turns out. So the first example is the following. Okay, in California, 39% of residents are Latino, 35% are white, 16% are Asian or Pacific Islander, and 10% are other races. Okay, you can go through all the different races, but that would take forever, so I just went here. Okay, and by the way, I looked these up. This one you can quote me on. You know, I mean, nothing's perfect, but I looked up, I don't remember, Google and then something, and it looked pretty reliable. So that's California. Okay. Is the distribution of races different for the California community college students? So that's important. You know, one of the things you want to look at is, are we discriminating, for example? You know, is it California community college discriminating and not Latin, you know, and kind of discouraging one race from coming in? Does that make sense? So that would be a reason why you would do something like this, because what you want to do is it'd be the best for the California community college system to have the same distribution as California of races, because then there's really no discrimination. Do you see? Okay. On the other hand, if we find out that the distribution is not the same, then you look deeper and you say, well, maybe we got discrimination, see who's getting discriminated against. Do you see? You know, who are we not letting in, or, you know, who are we not encouraging to come, that kind of thing. Okay. A survey was done of 300 California community college students, and 125 were Latino, 92 were white, 33 were Asian Pacific Islanders, and 50 were other races. What can be concluded at the 5% level of significance? So you should be used to this last sentence, because basically that's what we've been doing for weeks, right? And that's what we're going to be doing this week. And by the way, we're going to do that next week, and we're going to do the week after too. That's all we're doing. You know, next week we have some more stuff besides this. So what can be concluded? By the way, you don't even talk about confidence intervals for this kind of thing. It doesn't even make sense, because it's a bunch of different races. It's not like there's not an interval that does something. But you can talk about, you know, does the California community college student, is that representative of California? And that's what we want. Do you see how that works, or is it not? Any questions so far? Okay, so as I mentioned, unlike chapters 9 and 10, H0 and H1 are going to be done in words only. But I want to give you a big, you know, a big thing, big important thing. That's true for chapter 11. That does not mean that now in chapter 9 and 10 you don't have to use symbols. Okay, you still do chapter 9 and 10 the way you used to do them. We're not changing 9 and 10. So if you have a hypothesis test for proportion, or a hypothesis test for mean, or two proportions or two means, we're still going to be using the you know, like chi and mu. Does that make sense? But if we have a hypothesis test that is this kind of test where it's a qualitative variable, then there's not a letter that we use. So instead, we're going to use a sentence, and here's the sentence. The distribution of races at CCC, California Community Colleges, is the same as the distribution of races in California. And I want to let you know, I'm going to do this on purpose. I just took the word distribution, I put it in red. Any guess on why?
Because it's important.
It's important. And if you don't have that word when you're doing one of these chi-square kind of problems, what's going to happen?
Points will be taken off.
Yep, that's guaranteed. But let me guarantee something else. If you do have the word, then I guarantee I'll give you points, even if the rest is wrong. So at least you could have the word distribution. You should get some points just for writing that down. Now it's better if you actually understand the whole thing and write the sentence. But any questions on this? And I want to mention this word here, the same as H0, you're used to always having an equal sign, right? Right? The words for equal sign, it's the same as. Do you see? So that's something that's the same as the old days, but now we're just doing it in words. Okay, and if you can come up with some like really good simple symbols to write this sentence, let me know, but I haven't come up with any symbols that, there are symbols, but it's way too hard. Especially H1, it turns out, to write in symbols. H0, you can write symbols, but not H1. Okay, or it's tough for everyone. Okay, so we need H1 now. So the nice thing is once you have H0, H1 means that H0's not true. So what's the only change I need to make to H0?
Change the word same.
Yeah, I could change the word same, or what could I put in front of the word same?
Add not.
Or yeah, add the word not actually before the word the, probably for grammar reasons. Yeah, so I'm just going to copy and paste H0 and put in the word not. If you wanted to, you could also say the distribution of races at CCC is different, but then you say from the distribution of races in California, from because of grammar, not because of anything else. But when you're copying paste, not's a lot easier, isn't it? You know, but like I said, if you wrote they're different, that's okay too. But don't switch. Remember, H0, just like in chapter 9 and 10, always had the equal sign, right? So now we're always going to have the equal sign in words, so the same as. Okay, whereas H1, I told you there is no left and right tail, there's only two-tailed basically, and that's the not the same. And that's the same or different. Any questions at all on the H0 and H1 for this example? Okay, and I want to let you know, it's not always going to be races at CCC. It's not always going to be California. You know, you'll see different examples with different things besides that. So, but you'll always see the word distribution, always see the word same as, and always see not same as. Okay. Any questions at all on this? Okay. So now what we need to do is we need to start doing the statistics now that we've written the hypotheses out. So what we're going to do here is we're going to create a table. And this table is going to be the observed and expected table. So we call it the observed and expected table because it's what we observe and what we expect. So let me explain how I got all these things. So here's the table. I like to use O for observed, E for expected. Most people do. It's like the only time I use O as a one letter thing, because it looks like a zero, but it isn't. It's observed. Because what else could it be, right? And then the choices that people have in this survey are Latino, white, Asian Pacific Islander, and other. Does that make sense? And then we go ahead and look at the paragraph. There were 125 Latino, 92 white, 33 Asian Pacific Islanders, and 50 others. So 125, 92, 33, and 50. So there's your 125, 92, 33, and 50. Any questions on the observed? These are really easy. They're not easy in the real world, but they're easy in our class. Why are they not? Why is it the hardest part in the real world?
Too many people.
You're gonna have to go survey them.
Yeah.
And that takes hours and hours and hours, right? So that's why in the real world, that's really hard. You know, a test problem, you don't have to hours and hours and hours of surveying. But in the real world, that has to happen. Does that make sense? So the real world, that's the hardest part of the whole thing, but you won't notice that in this class because it's going to be given to you. Okay, expected. That's actually the easy part in the real world, but it'll be hard for some of you because you have to know how to do it. And there's a little bit of math, nothing too hard. So what we do is we say that Well, if California community colleges had the same race distribution as California, and we surveyed 300 students, then we would expect 39% of them to be Latino. Is that clear? Okay, so how do you find out the number that you would expect? Well, if you expect 39% and you survey 300, it's 39% of 300. Any questions on that? So 39% of 300, maybe I'll work it out. That's going to be 0.39 times 300. Any questions on that? And if you work that out, you get 117. Any questions on that? And then you do the same thing for the next one. 35% are white. So you do the same thing of 300, right? So 0.35 times 300. And that, if you work out, is 105. Okay, and then we had 16% Asian Pacific Islander. So 0.16 times 300. And that's 48. Okay, you could do it like I do, it's do it in your head, or you can use a regular, you could use a calculator. Most of you probably want to use your calculator. Okay, although the last one you might feel doing your head. Let's see if you guys can. What's 10% of 300? Yeah, that one, hopefully you can do. That one's 30, right? So 0.1 times 300 is equal to 30. And that's where I got the expected values. Any questions on that? All right. So now we need to get a p-value. The test statistic, by the way, is going to be chi-squared. That's why I spent a lot of time saying the word chi-squared. We need to get a p-value. Any guess on how we're going to go get a p-value?
Go to the calculator, a calculator.
Yeah. What we also need to do, before we even go to the calculator, is probably a good idea, is to name the test we're using. So we're going to use the goodness of fit test, often called the chi-squared goodness of fit test. Okay. And I think they call it goodness of fit. I'm not the one that named it, because we want to say, is the observed values, right, our sample, does it fit pretty well the expected values? Do you see that? Does it fit the distribution that you would expect it to be? And that's goodness of fit. Okay. And by the way, if you look at it, are the numbers the same? 125 and 117, are they the same numbers? No. 92 and 105, no. These are all different from each other, right? But hopefully you've now had enough statistics that being different from each other does not mean you can say that the populations are different from each other immediately, right? Because we only have a sample. And when you have a sample, then you're almost always going to have not exactly the same proportions as what you would expect the population to have. But you don't want to be that far off. So it turns out if you subtract these two, 50 minus 30 is 20. And the thing is 20 a large distance away from what you would expect. Okay. And you don't have to understand the mathematics of doing that, because that's what the calculator is going to do. But I want to mention that that's what the calculator is doing, is it's kind of looking at how far away relatively are the observed and expected from each other. And there's a bunch of them, there's averaging out, and there's like brutal math. But that's kind of what's going on, is say, you know, if you're really far away from what you expect, then you're going to have a high p-value. Whereas if all the numbers are close to what you expect, you're going to have a low p-value. Do you see? Because a low p-value means that H1 might be true, could be really the same distribution. A high p-value means that you're going to say H1 is true. You're going to conclude that with statistically significant evidence, and that means you're going to have a low p-value, small probability. So now we go ahead and go to the calculator. We're getting towards the end of the class, which means I have to scroll down towards the bottom. And what do you see? Any guess on which calculator number? I tried to make it really obvious.
21.
Yep, 21. Goodness of fit. And you're supposed to separate by commas. You're used to doing that. Unfortunately, it's in a table. So if I copy and paste, I'm going to have to put commas in there. But let's do that. Copy, paste, put some commas in. And then same with the expected. Copy, paste, put some commas in. Okay. And by the way, you don't have to do a confidence level because there's no confidence interval with this stuff. So there's not much you have to do. You just have to put the data in, observed and expected, and hit calculate. And what do we see? We have our chi-squared, which is around 20.177 or so. Let's write that down. And the p-value is tiny, 0.000156, rounded. Any questions so far? Okay, and the hope is that you have understood enough of chapter 9 and 10 to know what it means to have a p-value of 0.000156. Notice I didn't even bother giving you, maybe I did, but I did give you level significance, but I didn't really need to give you level significance. Not with this kind of p-value. When you have a p-value of 0.000156, what do?
You reject.
Yeah, you reject the null hypothesis, okay? And by the way, it's very strong statistically significant evidence because that's a tiny, tiny p-value. Okay, you're below 0.01 even, right? Even 0.001. So that means we can start with there is strong or very strong statistically significant evidence to conclude that, okay, any questions so far? The hope is what I've written is what you're used to, and you would know to at least write that part. And the good news is, now all I have to do, because we have it in words already, is copy and paste H1, because that's what we get to reject means you say H1 is true, right? So I can copy H1, paste it, and I guess I need to not let the be capitalized. That's grammar. And probably don't need that in red anymore because that was really for, just showing you. And we could say there is very strong statistically significant evidence to conclude that the distribution of races at California community colleges is not the same as the distribution of races in California. Any questions on that? By the way, does this tell you which race is different from what you would expect? Yeah, this doesn't. So here's what I'm going to tell you, and I'm going to be telling you a lot in the next few weeks. The same thing, and that is, first, do you think there's a way to find out which race is the one that's, different? Okay, it turns out there is. But I'll also tell you that if you want to find out how, what you need to do is you need to take an upper division statistics class at a university, because it's beyond what we do in our class. It's not hard math, but it's just the next level of statistics. There's elementary statistics, and that would be that next level, intermediate or advanced statistics. So just because in our class, we can't say which races are different from what you expect, doesn't mean it can't be done. It just can't be done using elementary statistics. Is that clear? Which means you're not responsible for it today. But if you get a master's at a university, you might be then. Because then for your master's, you're going to have to figure that stuff out. Okay, I don't mean in math. I mean, that could be in psychology or, something like that, or nursing or whatever. Okay, because that stuff has to be done. Any questions on the chi-squared goodness of fit example here? Kind of clear? Okay, and this stuff's used a lot. This stuff is used a lot. All right, here comes the next example. Okay, does it matter what season a person was born in when it comes to the type of car they drive? Okay, I was a summer baby, by the way. I'll tell you that. So the table below shows you the season and car type. Okay, and we have spring, summer, winter, and fall. And we have sedan, SUV, and other. So notice, by the way, the survey questions here, the first would be, what season were you born in? And I say, summer. And the second question would be, what kind of car do you drive? Right? And I would say, SUV. Do you see? So that is how these work when you have qualitative survey questions. And now there's 2 qualitative survey questions, not 1. Then we're going to have a table like this. And notice the goodness of fit will not work. Goodness of fit is when you only had 1 survey question, right? Right? In the example we just did, the survey question is, what's your race? Is that clear? And you might say, I'm, Caucasian, or I am Hispanic, or I'm African-American, or whatever. Does that make sense? Right? But it's a single survey question. This is 2 survey questions where they're both qualitative. Okay. Notice these numbers are not the answer to the survey question. This 76, what that means is 76 of the people that you asked were born in the winter and drive a sedan. Any questions on reading the table? Okay. So here, what we might want to say is, if we know somebody was, say, born in the spring, does that mean they're probably more likely to maybe drive an SUV? Given when they were born, does that help you understand what kind of car they drive? Okay, or vice versa. If you happen to know what kind of car they drive, could you get a good guess on when they were born? Any questions on that? And that might be true, might not, right? I will tell you, just for, to let you know, I made up these numbers, but a survey like this could be done. It wouldn't be, it would take a lot of work to ask a lot of people, right? But other than that, it's not that hard. Is that clear? So this is a survey that could definitely be done, and see what happens. And this kind of stuff is done a lot where you're looking at 2 qualitative questions and seeing, is there a relationship or not, right? So the word we use is, are they independent or are they dependent? And we're going to use what we call a chi-squared test for independence. And that is when we have 2 survey questions, they're both qualitative, and we want to say if they're independent or dependent. So the chi-squared test for independence. What I have found when I talk to students is that the hardest part of this chapter? Any guess?
The wording?
That's usually not, actually. That's not what they say. Or the errors they make. The hardest part actually is to decide which test to use. Whether after reading the paragraph, is this independence or is this goodness of fit? And then we'll have a homogeneity in a bit. That's where people have the hardest time. And the best suggestion I have is practice. You just practice a bunch of problems from chapter 11, and then you'll start getting used to where it comes from. And then it gets even harder, as we go, because then we have more and more hypothesis tests, more types of things. And you have to kind of figure out what to do. That's what people have the most trouble with. Okay, so we need an H naught and an H1. So what H naught is going to be is season, a person was born in, and car type are independent. Okay, I want to take that word independent, and I'm going to put that in red. And hopefully you know why. That must be in your H naught. Any questions on what H naught is? In H1, the good thing is I can do something really similar. Copy, paste, and I'm going to change the word independent. Make it a little shorter. What should I do?
Change it to dependent.
Exactly. You can change it to dependent. So season a person was born in and car type are dependent. And that's H naught and H1. They're always going to look the same because you're always going to have two survey questions that ask for two different, items from the categories. And you say the first and the second are independent, that's H naught. The first and the second are dependent, that's H1. So that's why the wording actually isn't that hard. Does that make sense? Yeah, this is not the hard wording one, but you have to know that it's independence. That's what we're doing. Okay. It turns out we have had questions about independence before. What chapter was that from? I know, it's been a long time. That's a hint. Where you had to decide if two things were independent. And remember?
I'll guess 3.
Yep, it was 3. Good guess.
Was it?
Yeah, it was chapter 3 when we did probabilities. And we decided whether things were independent or dependent. And I will let you know, the deep math behind all this stuff uses what we did in chapter 3. And then a whole lot more to make combining table all together instead of we just looked at like winter and sedan instead of the whole thing. So now we're doing things, now it's much more abstract than what we did in chapter 3, which in a way makes it easier because you don't have to decide which ones and all the different formulas and all that. You just test for independence and you're done. Any questions on this? Okay, so now that we have a chi-square test for independence, what I'm going to do, any guess?
The calculator? Calculator?
I'm going to go to the calculators, this one, and I'm going to go back to the calculator menu. Scroll towards the bottom because we're towards the end of the class. And what test are we going to use? It should be really obvious.
22.
Yeah, 22. Test for independence. Any questions on this? Okay. And this one, I can't do separated by comma things because it depends on, there aren't just 2 things to put in. It could be many. So this is where you have to actually create a table. I will let you know kind of give you a heads up. I made this when I programmed this. So you can't have, say, a 5x5, it won't work. This particular calculator, because it only allows 4. You could have, say, an 8x4 or even a 10x4, but nothing bigger than that in either direction. Does that make sense? It turns out if you want to do, more like a 10x10, then I did create in my spreadsheet calculator. That can be done, but that's never going to happen in our class. But just let you know, after this class, if you need, say, a 10x10, don't use this calculator because it won't work. But I'll never ask you anything worse than, where the minimum number will never be bigger than 4. Otherwise, it's just too much typing. Does that make sense? So I don't want to, I'm not here to torture you. It may seem like it sometimes, but I'm not. Okay, so now we just got to remember all the numbers. 73, 81. 76, 78. 65, 68. 62, 64. 43, 51. And then 48, 50. Any questions on just putting in the numbers? Leave everything else blank. And hit calculate. Okay, and you get chi-squared is 0.48 about. In your exercises, I would keep 4 decimal places or 5 decimal places, not 2, but we can get away with it here. And the p-value was 0.9981 maybe. So if we have a p-value of 0.9981, what does that tell us?
That we're going to fail to reject.
Yeah, so we're going to fail to reject. That's about as big a p-value as it gets. Okay, so that's like a super fail. So that's one of those where you wouldn't even think about doing a larger sample size because it's kind of hopeless at this point. Does that make sense? Okay, so that's just a note. Okay, so the p-value is 0.9981, which is less than any level of significance. I don't know, did I even give you one? Not even give you a level of significance because you don't need one because you would never, ever, ever accept accept H1 or reject H0 when you have 0.9981. It's just never going to happen. So first few words. Yep, I'll remember this. So first few words. Hopefully you all know the first few words. We're doing a hypothesis test here. A very large p-value.
There is insignificant evidence.
Yeah, I usually write the word statistically.
Okay.
Insignificant evidence to conclude that, and I can just copy and paste H1. And then, of course, I need to make the word season lowercase for the grammar to be good. And I guess it wants a the. Yeah. And dependent probably doesn't need to be in red. That the season a person was born in and car type are dependent. Any questions about a chi-squared test for independence and the whole thing on this? Do you see why, if you know to use the chi-squared test for independence, this isn't that hard, is it? Yeah, and once you write H naught and H1, it's actually really easy to write the conclusion. Any questions at all on this idea? Okay. And this stuff is done a lot, by the way, just to let you know that a lot of times you're going to be looking at this independence dependence in the real world. Okay, so here's the next one. Is do single men and women take the same type of vacation? Okay, the table below shows the results of the study. So here is the men, and we looked at international, out of state, or more local. Okay, and the men, 29, 47, and 33. So that would mean 29 of the men said they, last time they traveled, they went international. And 47 of the men said last time they traveled, they went out of state. Okay, travel for vacation. And then the 33 of the men said last time I had a vacation, I just didn't go very far. Just stayed in California or stayed in my state. Does that make sense? Okay. And then the females, the women, same idea. Any questions on this? All right. So at this point, what we're doing is we're looking at two different groups of people, the men and the women, and we're saying, do they have the same distribution as each other when it comes to how they travel? Do you see how that works? Because that's what we're interested in. Okay, so this is a lot like goodness of fit, but instead of having one population that you don't know and comparing it to some distribution you do know, we have two populations we don't know and we're comparing their distributions. So the name for the test we're going to use is a chi-squared test for homogeneity. Have you heard the word homogeneity before in your, in other things? You probably heard variants of the word homogeneity, like homogenized milk, right? What's homogenized milk? You don't know what it is. You've heard of it. Yeah, it means they've put all the stuff in there together. Okay, so yeah, homogeneous. There's kind of homogeneous and heterogeneous. You hear those words? This isn't math, this is English. But it's hard English. Hard English isn't necessarily easy either, right? Okay, so, and so homo is the same. And hetero means different. So that's something that, you might have heard that before. So the question is homogeneity. Are men and women the same when it comes to their type of vacation? Do you see? And that's why the word homogeneity. Again, I'm not the one that came up with it, but I want to explain where it's coming from. But it looks like, at least from from your looks, you don't really know what those words are anyway. So, but now you do. Not just math. It's not just a math thing. It's a good word to know. Okay. So we need to have an H naught and H1. And now what we're going to do is it's going to look a lot like the goodness of fit, but now we have really two different distributions that we don't know. So we can write the distributions of vacation type are the same for men and women. Any questions on that? And let me do the following. Take that word distribution, put it in red. Because now we have two different distributions, not just one that we don't know. We don't know the population of all men. We don't know the population of all women. Not going to happen, right? You can never get everyone, okay, or every man and every woman, okay? So that's why it's in the hypotheses, something we don't know about, okay? And we don't know either, so they're both happening. We do plural. And I bet you can guess the one small change we need to make for H1. One extra word.
Add in not, the same.
Yep, exactly. Add not before the word the. So I'm going to do it the lazy way. I'm going to copy and paste. And for the word the, I'm going to put not. And I could say the distributions of vacation type are not the same for men and women. Any questions on that? Okay. And again, I want to give you the heads up. These numbers I totally just made up. I didn't really do a study but you could imagine doing a study, right? This wouldn't be a hard survey question to ask or anything like that. Okay, but I made these up. Okay. So the test again is the chi-square test for homogeneity. So I need to type that in again. That's the test. Okay. And you should be able to write down which test you're using, by the way. The words. You are responsible for the names. Got it? So I know there is no exam this week, but there will be one next week. And the week 10 exam, I'm going to ask you to write down the name of the test you're using. So you have to be able to identify the test. And in this chapter, we have 3 tests. We have chi-squared test for goodness of fit, chi-squared test for independence, and chi-squared test for homogeneity. Any questions on that? Okay. Notice this one looks, in terms of the table, it looks a little more like the test for independence than it did the goodness of fit, because we don't have observed and expected. We just have 2 groups. What makes this a homogeneity is we want to say, are men and women different from each other? So we're looking at 2 populations and looking at their distributions of vacation type. Okay. Instead of saying, are gender and vacation type independent? So it has to do with really the focus on what you're doing. Turns out that if you put it in the independence calculator, you'll actually get the same answer. But it's important to still have a homogeneity calculator to remind you that the focus is different, even if the math is the same. So I'm going to go back to the calculator. And what calculator do you think we're going to use?
23.
23. Okay, and just a note, other than finals week, how many more weeks of this class do we have? Should be easy looking at the calculator.
2.
2. Guess what we're doing next week?
Regression analysis.
And guess what we're doing the week after?
ANOVA.
Yep. Yep. And that's it. And then we have our final exam, basically, and that's it. Which is actually unlike other finals, it's an easier final because it's only 10% of your grade. So easy in terms of less stressful. So week 12 is the easiest week of the class. That's not normal, but one reason I do that is that if you're an LTCC student, then your other classes are kind of brutal finals week because you're really stressed. So you know at that point you kind of know what your grade is. 10% could change a grade by one grade, but not any more than that, right? So that's just a note. So we're almost done. Okay, we have regression analysis, which is really important, by the way, in terms of the real world stuff. And ANOVA is really important in terms of research. So that's what's coming at us. But we're doing homogeneity this week. We have 3 different tests because they're all pretty easy. Hopefully you agree. These aren't so hard, are they? And I usually give you a warning when they're easy to watch and hard to do, but most people don't think these are hard to do either. Okay, so now we need to put numbers in 29, 47, 33. Okay, and the way this table is, it's vertical numbers, even though I showed you horizontal. So that's just a note. And I did that just because it spaces better on, a computer, especially a smartphone. And then we have 38, 42, 36. Any questions on putting the data in? Okay. And by the way, if you have a bigger sample, then I don't remember how many of these are. That's 3, 6, 9. If you had a bigger sample than 10, then this calculator will not work for you. So what would you have to do? And when I say sample, I mean not a sample size. I mean if you had more than 10 different choices. So like what state were you born in? There's 50 different choices. Any thoughts?
You said something about the spreadsheet, the Google spreadsheet.
Yeah, so my spreadsheet does everything, by the way. I don't know if you realize that. It does everything, but it's more sophisticated, so it's a little harder to use. So with the calculator, it's a lot simpler, but it's not as, calculator's not as good for some of the research that might happen like after this course. But for this course, it'll work for what you need. But if you had like, what state were you born in? This won't work because there's more than 10 states in America. Hopefully you know that at least. Yeah. But from anything we're going to be doing in our class, we're not going to have more than 10 choices. Just too much typing. And I say calculate. Easy enough. And the chi-squared is 1.4. The p-value was 0.496, rounded. Any questions on that? Okay. So first few words of the conclusion. You better all know.
There is statistically insignificant evidence.
Yeah. So there's statistically insignificant because the p-value is 0.496, which is bigger than any level of significance you would ever have. Notice it doesn't give you level of significance. So if you don't have a level of significance, which is true in the real world usually, by the way, then you use language. So remember, anything bigger than 0.1, you just say there's statistically insignificant evidence. If it's between 0.05 and 0.1, you would say there's weak statistically statistically weak evidence, because it's there but not great. If it's between 0.01 and 0.05, you would say there's statistically significant evidence. If it's under 0.01, you usually say there is strong statistically significant evidence. That's kind of the grammar, the language you use. And we've seen that before. So it's the same stuff. To conclude, that. And then, as we've been doing pretty much for this whole chapter, copy and paste H1. And then make the lowercase. And we don't need it to be red anymore. And when I copy and paste, it changes the font size, doesn't stay good. So there we go. I would never take off points because your font size changed. But there is statistically insignificant evidence to conclude that the distributions of vacation type are not the same for men and women. Okay. So just to note, this does not tell us which gender goes to which vacation more or less. Does that make sense? All it does is to say that men and women have different distributions of vacation type. Okay, we can't say what's the reason for it. Do you see? And as I mentioned from before, in the last one where I said that, it can be done, but you need more advanced statistics, which is beyond this course. So there's gonna be a lot of that where, you might be interested in finding out more information and, better reasoning and all that, but we can't do everything. Okay, I don't usually have a lot of students saying, we really should have covered more material in the class. We didn't really do anything. So you could have added a whole bunch more topics. That's not usually something people tell me. But I will tell you, what I do is I go to conferences. I talk to other community college faculty that teach statistics, find out what they teach, and then try to make sure that my class is just like theirs. So the idea is that there should be, you're going to love this word, homogeneity. There should be homogeneity in our teaching, right? Okay. Not everything we do, but definitely the topics. Okay. And it's gotten to the point where part of it is because of me and they all follow me. It's a little weird because I do this online stuff and everyone copies my class now. So just let you know. So if you take another college, you'll get the same curriculum. Okay, but if you take an upper division course, that's totally different because that's not beginning statistics or elementary statistics. Any questions at all on these three examples? Okay, let me do one more example because it's one we've talked about a lot. Okay, a study was done asking people how far they plan on traveling for Thanksgiving. Okay, so, that was a few months ago. And the question is, how far do you travel for Thanksgiving, right? For our next Thanksgiving, how far do you plan to travel? Does that make sense? The mean was found to be 120 miles. The standard deviation was 40 miles. Okay, the table shows the results. Is the distribution normal? Okay, all of a sudden, this is totally different than anything we've done before. Okay, the survey question is qualitative, by the way, right? Okay, if you ask me how far I plan on traveling for Thanksgiving, if my sister's having it, then it's about, I think, around 200 miles or so. That's how far I'll be traveling. Okay, it's a number. Okay, does that make sense? So this is different, but the question is the important thing. right here is the distribution normal. Do you see that? So the question is the distribution normal. So what I'm going to do is I'm going to break this up into 3 different pieces. Less than 80 miles, between 80 and 160 miles, and greater than 160 miles. Okay. Notice 120 is the mean. If you add the standard deviation, which is 40, what do you get?
You get 160.
Yeah, there's that 160. If you subtract 40 from 120, what do you get? Not supposed to be hard. That's not a tough question. Should be able to do that in your head. 12 minus 4.
$80.
You get 80. Okay, and shouldn't be surprised. There it is. All right, so this right here says you're within 1 standard deviation of the mean. This here says you're less than 1 standard deviation, or you're more than 1 standard deviation below the mean, is probably the way to say it. And this right here is you're more than 1 standard deviation above the mean. Any questions on that? Okay, so we can use the empirical rule. What percent, if it's a normal distribution, because that's what we want to look at, what percent would you expect to be within 1 standard deviation of the mean? Now you got to remember the empirical rule. It's been a little while, but not that long.
Was it 90?
Not 90. Good try. 68. Does that ring a bell?
Yeah.
That was the empirical rule. Is that if you're within 1 standard deviation of the mean and it's a normal distribution, then 68% of that data lies within 1 standard deviation of the mean. Any questions on that? Okay, so if there's 68% inside, there's 32% outside. If there's 2% outside, there's 16% on the left. Okay, so if we take 16% of our sample size, for the sample size, we just add these numbers. 56 plus 61 is 117, plus 12 is 129. You can use a calculator if you want. So our sample size was equal to 129, just adding the 3 numbers. So our expected less than 80, to find that out, we just take 129, and that should be 16% of that. Anyone lost on what I just did? Any questions? This is the hardest part of the whole chapter, probably, is understanding how this stuff works. Okay, so we got to bring that empirical rule that happened and all that, calculating probabilities and using the normal distribution. Happened to, chapter 6, then a little while ago. Okay, 0.16 times 129, probably want to use a calculator. And I get 20.64. Let's round, call it 21. And by the way, 16% left, so 16% right also, because normal distributions are symmetric. So we have expected 21, 21. We could take 68% of 129 to get the expected in-between values. Or I could say I got 42 already that I've grabbed over here. So I just subtract 42, 129 minus 42, which is 87. You don't have to do it in your head. But that's what I did. I just took 129 minus 21 minus 21. Any questions on that? Okay, all of a sudden, now what does it look like from what we've already done today?
Goodness of fit.
Yeah, this is a goodness of fit test. Do you see? So we can use a chi-squared goodness of fit test to get an idea of whether the distribution is normal, which we've seen was really important. A lot of times you have to assume the distribution is normal. So now we could say, well, is it even reasonable to assume it? Do you see? And if you get a really low p-value, you'd say, nah, this assumption is just way wrong. Whereas if your p-value is really high, you'd say, okay, normality could happen. Do you see how that works? So wanting to know if something's normal actually is important, especially if you have a small sample size, right? Okay, so now we can go ahead and we can go back to the calculator menu. Scroll down, goodness of fit. We have the observed and the expected. So I'm gonna 56, 61, 12. And then 21, 87, 21. Any questions on that? And I calculate. Okay, and our chi-squared is about 70. Oh, I didn't put all this in. Sorry, let me do this. Goodness of fit. Our H naught is very simple. The distribution. Goodness of fit. So you get how that word distribution of travel distances. Let me go Thanksgiving travel distances. Is normal. Wasn't that easy? And then H1, I can just copy and paste. The distribution of Thanksgiving travel distances is not normal. Any questions on that? The chi-squared I got was, again, about 70. Is a p-value about 6.66? P-values can never be bigger than 1. The answer can't be 6.66. If you think it is, you're not moving your eyeballs far enough. What is the p-value here? Here's a hint.
10?
Not 10. No, it can't be bigger than 1. P-value is never bigger than 1. Because it's a probability. Probabilities can't be bigger than 1. Okay, what does that E negative 16 mean? We've seen it before, or something like it.
Is that how many decimal places there are in the front?
Yeah, Yeah, how many, not how many decimal places, but how many
Zero.
decimal places to move that decimal point. The first move, nothing happens. All the other moves, you get a 0 out of it. So it's going to be 15 zeros before that 6. So you can actually put it in here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then 666. Basically, it's about as close to 0 as you will ever see. What does that tell us?
That we reject the null.
Yeah, and there's no way this is a normal distribution. You see that? Because look how small this p-value is.
Yeah.
Okay, so there is extremely strong statistically significant evidence. To conclude that the distribution of Thanksgiving travel distances, and actually I can just copy this in, is not normal. Okay, notice this doesn't tell us what the distribution is. We just know it isn't normal. It doesn't say it's uniform, it doesn't say it's bimodal. All it tells us is it's not a normal distribution. There. Oh, it even knows. Any questions on this goodness fit? I want to do this type because it's looks a lot different than the other one, doesn't it? So I figure you should get both types as an example. Okay, so those are that is pretty much chapter 11, which means we have our secret word. And the secret word is distributions. And if you don't know why I chose this as a secret word, then you're not paying attention. Okay, for homogeneity, it'd be distributions. Goodness fit distribution. And I chose distributions. So distributions, because that's the word you have to have for homogeneity, basically. So as I mentioned, it's a little shorter today than usual because there's no extra stuff to talk about. This chapter isn't known as the hardest chapter, so I don't have to spend as much time. But that doesn't mean I can't answer questions. What I'm going to do is I am going to stop the recording.